Greetings everyone and welcome back to the bench. In this video I'm going to talk about setting up the LM380 properly so you get the most power, least distortion, and no problems with the oscillating and things like that. That can occur when the amplifier chip is not set up properly on the circuit board. Before I begin, I want to give a big thanks to everyone who sent a really nice comment about my brother. If you haven't seen it, I put a channel comment about my brother's cancer situation. They found cancer in 3 different parts of his body, and that was kind of a shocker to hear that news. Right now they're in the discovery stage. They're doing all the tests, the biopsies and all that stuff to figure out exactly what kind of cancer he has and what measures they need to take. But really do appreciate all those kind comments. Thanks a lot for that. Okay, so we have the LM380 data sheet here, the 2.5 watt audio power amplifier IC. And this is kind of like a beefed up version of the LM386, and when we take a look at the internal schematic you'll see quite a bit of similarity there. Now this chip is quite old. I thought it was maybe in the mid-70s, but I found an applications data sheet that's from December of 1972, so this chip has been around quite a while. And the interesting thing is you can still buy it. It's still available. And there's another version of this chip, the LM384, which is identical except that it can run at a higher voltage. Okay, some of the features here is a wide supply voltage range, 10 to 22 volts. I'm not going to go through all of these, but high peak current capability, 1.3 amps. The LM386 isn't specified, but I know it's quite low. It's probably around half an amp from experiments I've done on the chip a while ago. So yeah, it kind of peters out when you load down the output of the LM386. So this should be able to handle the higher voltages and even 4 ohm loads in some cases. We'll take a look at that. Fixed gain. Also features short circuit and thermal protection. The chip's most common package design here is this 14-pin dual inline package. Also comes in an 8-pin dual inline package. I don't know why they did this, because at the voltages you would want to run this at, it would get very hot with 8 ohm loads. I guess it would work if you wanted to use 16 ohm loads, but heat dissipation becomes a liability in this small package. Whereas this package, the center 3 pins are tied to the internal copper pad inside the package that the die is connected to. And those pins can be used to help draw away heat by using a foil area on the bottom of the board. Here is the internal schematic of the LM380, and if you watched my LM386 video you know these are quite similar, but there are differences. Well, you have your differential input stage here with the current mirror, and you see you still have those biasing resistors. Current is flowing in here, and for this input stage to turn on you have to have some current passing from the emitter to the base of these transistors, and you have to have that resistor there. So to save parts, external parts, they put that resistor on the inside of the chip so you don't have to worry about it. On the LM386 it is a 50k ohm, and on the LM380 these are 150k. So that allows the input impedance of the LM380 to go somewhat higher. Now I know some people like to make guitar amplifiers out of the LM386, but the LM380 might be a little bit better because it has higher input impedance. Of course you can add a preamplification stage with higher impedance, but if you want to keep it simple and just use the chip, this might be the way to go, because you also have the ability to run it at a higher supply voltage. and you'll be able to get more power out of it as well. But the same situation is true here as it is with the LM386. I see a lot of circuits where the unused input is connected directly to ground. And what happens is, this is normally balanced because you have the same value resistor. So if you just take the unused input and ground it, that increases the current in the side of the input stage that you grounded, and it throws off the output a little bit. In other words, the output swing will clip on one side before the other because the 0 point of the output's been thrown off just a little bit. And I'll demonstrate that when I hook up the chip to the oscilloscope. I'll bypass one of these resistors by shorting the input to ground, and we'll see how it affects this. So what can you do? Well, just like the LM386, you can either leave the pin open, which is not recommended because with 150 kiloohms of input impedance, the input's going to act like an antenna and pick up noise. Instead, you can just bypass all of that with a capacitor, so the DC will still flow through the resistor and it won't offset the output any. There's another difference of how this chip is set up as compared to the LM386. You see, this ground here, all these parts of the circuit come to this pin 7 ground. The output stage comes to the heatsink ground pins, and they're all numbered here. The reason for doing that is it just makes it simpler to bring all the small signal grounds to one pin and the large signal from the output stage to another pin. That allows you to set up the circuit so you're not running the heavy currents from the output stage into the smaller signal stage, and that could cause distortion or oscillation. But it's important to understand that both of these pins are still connected to ground, or the negative side of the supply, or the amplifier won't function. Okay, here is my recommended circuit. It's just a simple non-inverting audio amplifier circuit using the LM380, and here's the additions that I've done. I've added a low-pass filter on the input that keeps RF out, and because the amplifier's input impedance is so high, it could actually pick up its output and oscillate, so this helps alleviate that problem. And as I mentioned before, I'm not connecting the inverting input directly to ground. I'm bypassing it with a capacitor to ground so it doesn't offset that bias current flowing through the internal 150K resistor. And I'll demonstrate by shorting this capacitor, in other words, shorting the pin directly to ground, to see how it affects the output. And here's the board layout of this circuit. These pins here are the IC. This would be pin 1. And this shaded area is the copper foil, which is connected to those center 3 pins to help with heat dissipation. Now this is the component side of the board, so you're looking down through the board to the traces. And I do it that way because it just works easier for me when laying out the board. And here's the actual board. It's laid out just the same. I think one resistor's moved because I just didn't have room on the smaller board. So it's pretty much the same. I ran the wires through the holes to act as a strain relief so they won't break off because I'm going to be moving this thing around. So what I'll do now is hook this up to power supply, scope, and put a load on it. We'll run some tests. Give you a little music sample as well. I'll even compare it to the LM386 to show you that it's better to use this than the LM386 when you're going to run it at higher voltages, even though there are LM386 versions like the N-4 suffix that can run at higher voltages. If you're going to use 8 ohm loads, it's better to use the LM380. Okay, the amplifier is hooked up to the music source, going to the preamp. I just used the preamp because it has this volume control, it's easy to adjust rather than the stepped one on this. 12 volt power, and we'll give you a little music sample here. There you go, some music courtesy of the YouTube library. Safe to use without getting flagged. I notice now I'm starting to get flagged on some older videos. What they're doing now, the rights owners, are going through and manually finding music in videos and flagging it. Absolutely ridiculous. Only have just a few seconds of music and they're going in there and flagging your videos. Are they that hard up for money? But anyway, let's go ahead and hook this up to the scope and put the resistor on there and do some measurements. Okay, I'm hooked up to the 8 ohm non-inductive load. We'll take some power measurements. See, we're into clipping there. So we'll tune it out of clipping, get it as close as I can. That looks good right there. We'll say 2.9 volts. 2.9 squared divided by 8. So we're getting 1 watt, which is good. That's not too bad. So what I'll do is continue taking power measurements at different supply voltages, and I'll regurgitate the results at the end of the video. But now I'll show you what happens when you short one of the inputs directly to ground without using the bypass capacitor. Okay, so now I shorted it to ground and you can see it's clipping on the top. And that is going to cause us not to get as much power output because, you know, to get a clean reading I now have to turn the signal level down. So let me do that. Right around here. So now we're at 2.75 volts, we'll say. 2.75 squared divided by 8. So it did impact the power a little bit. We're now at 0.95 watts, and before we were just over a watt. 1.05. It's not a big difference, but it's just a little bit more headroom you get before clipping. Another thing I noticed with this chip, it always had a little problem with oscillation. It looks like it's oscillating just a wee little bit there. It was worse on the breadboard, but you know, I have a pretty good layout here. So, yeah, it's just a function of this chip. I don't think it could be completely eliminated. So yeah, if I turn up this, move this up here, yeah, there is a bit of oscillation going on right there. That's a very high frequency. I can play around with it, see if I can get rid of it, but I don't know. It's I don't know if it's worth messing with. It's so small, there's no way it would impact the sound quality. It's just something I've always noticed with this chip. Okay, we're taking a look at distortion here with the FFT mode on the oscilloscope. This is our 1 kilohertz fundamental. This is the 4.5 kilohertz pilot signal, which is at 1% of the amplitude of the fundamental. And I add that in there so it's a reference that I can see the harmonic blips. And of course, being at 4.5 kilohertz, it's non-harmonically related, so it doesn't cover up any of the harmonics the amplifier generates. And you can see here that there are some small blips. We have a second, a third, nothing really at fourth, but there's a little blip of a fifth. You know, nothing serious, but you know, these aren't hi-fi chips. So it's probably like 0.3 or so %. Okay, we're running the 10 to 100 hertz sweep. Right here is 20 hertz. It should be at this top and this bottom graticule here. And you can see that it's not quite there. Mainly due to the output coupling capacitor. It's 1000 microfarads. You can use a larger one, but at some point it becomes ridiculous. So it's almost there at 60 hertz. Okay, we're running the 20 to 20 kilohertz sweep, and it's going to be pretty flat. Now my music player does swell and shrink a little bit. Its frequency response is not perfect, but it should stay around that graticule all the way up to 20 kilohertz. Okay, it recycled, and yeah, the frequency response is pretty flat all the way up to 20 kilohertz. It's just at the lower end where the impedance of the output coupling capacitor comes into play and rolls off the lower end somewhat. Okay, the results are in. I took this LM386 board that I tested in another video, and I wanted to compare it at some voltages to see what the output power was. Okay, first for the LM380, here are the supply voltage levels, and this is the output power into 8 ohms. So at 20 volts, we got up to 3.32, and at 12 volts it was doing 1.05 as we measured. I measured at 12.6, which is a common battery voltage. So you can see it did a little bit better. At 4 ohms, it started out at 10 volts, 1.16 watts. With 8 ohms, it was 0.68. So you can see there is some benefit there using 4 ohms at 10 volts. And at 12 volts, we were getting about 1 watt with 8 ohms and 1.65 with 4 ohms. But notice at 12.6 volts, we were getting 1.28 with the 8 ohm load, and it only increased a little bit with the 4 ohm load. That tells me the amplifier is starting to struggle to deliver current when using a 4 ohm load. So that's as high as I took it. I wouldn't recommend running the amp at any more than 12 volts with a 4 ohm load. The chip starts to get stressed. Another thing I did is compare it to the LM386 and got some interesting results. With the LM386 at 10 volts, it actually put out a little bit more power than the LM380. The reason for that is the LM386 is just optimized for lower supply voltages. But you can see what happens here when we go up to 12 volts, the LM380 takes the lead from the LM386 now. And I went ahead and did one more voltage. 12.6, the LM386 starts to lag behind even more. You can see it doesn't increase much, telling me that the LM386 is starting to struggle. Now, before a million people in the comment section start telling me that the LM386 has the different suffixes for different supply voltages, I've tested those chips before, and they put out the exact same power than the lower voltage chips. It's just that you can run the LM386 like the N-4 at higher voltages. However, you have to use a larger impedance load because the LM386 in its tiny package just cannot dissipate a lot of power. So you can use the LM386 N-4 with, say, 16 ohm loads. But I really wouldn't push the LM386 any more than maybe 10 or 11 volts. It's starting to struggle at higher supply voltages. So just wanted to make that comparison. I was kind of curious myself how those two chips would compare. So there you have it, the LM380, certainly an old amplifier chip. It's still a pretty decent chip to use, even though it does have its flaws. Well, that's it. Thanks for watching. Well, hello there, Snickers. I knew I'd find you in one of your little sleepy spots. Uh-oh, something's coming to get you. Something's coming. Uh-oh. Uh-oh, it's coming through the hole. Got the kitty. Got the kitty. Got the kitty. So I'll continue to take voltage. God, I just can't even, I can't get this out.